Okay, in this video we're going to look at DC circuit. Right. So first we need to look at the circuit symbols. Right. So what is this? If this is a battery, and what is this? Okay. How about this? And this. Okay. So this is a cell. This is a battery. This is also a battery. And this is a variable power supply. Okay, and this is a resistor, variable resistor, light dependent resistor, LDR, light dependent resistor, and this is a thermistor. So we're going to look at the function of this and this in the following part of this chapter. Okay, you are given like this is a switch, lamp or bulb, LED light, emitting diode, and this is a diode. Then you have electrical measuring uh, tools or appliance such as the ammeter, voltmeter, and galvanometer. Sometimes you might see something like this. You see a prefix in front, it is a milliammeter. So these are some of the electrical measuring tool. Okay, so first thing, the most important under this chapter is called the Kirchhoff's law. So there are two laws, the first law and the second law. So let's look at the first law. So the first law, what does it state? The sum of current entering a junction is equal to the sum of current leaving that junction. So this is based on principle of conservation of charge. Okay. And example, if let's say you have I1, I2, I3, I4. So based on the principal conservation of Kirchhoff's first law, I1 plus I2 is equals to I1 plus I2 equals to I3 plus I4. Okay. So example, say now you have 5 ampere and here you have 10 ampere and here 7 ampere. So what is this value? So I1 plus I2 5 ampere plus 10 ampere. So we have I3 7 ampere plus let's say I4. So therefore I4 equals to 15 minus 7, 8 ampere. Okay. Right, let's move on to the next part, which is the Kirchhoff second law. So Kirchhoff's second law states that the sum of all the EMF in a closed circuit is equal to the sum of all the potential difference PDs in that circuit. So for example, let's say we have two resistors here. This is, let's say the EMF is 10 volts, right? And say the current is 2 ampere. This one is 2 ohms. This is 3 ohms. So what will be the potential difference here? V1 and V2. Okay, let's see. So total EMF is 10 volts, which is equals to total potential difference. So we have V1 plus V2. So we can write 10 equals to V1 plus V2. As we already learned, V is equals to IR. So I is the current, 2 ampere. Okay. Times 2 plus 2 ampere times 3 ohms. So 4 plus 6. So 10 equals to 10 volt. That means the EMF is equals to the potential difference V1. So we can use this Kirchhoff's second law to find out the individual current. So this will be 4 volt and 6 volt respectively. Right? So if you are given a circuit, something like this, EMF 1 and you have resistor R1 and you have another resistor EMF, source of EMF, and this is R2. So we have E2. Now the first thing you have to do, you have to verify the terminals. This is positive, this is negative, positive, negative. That means the current is traveling in this direction. Okay, so once you have verified total EMF is E1 plus E2. We can add both EMF, which is equals to V1 plus V2. So we can say that here is V2, here is V1. Okay, and say the current passing through is I. Therefore, I R1 plus I R2. So I equals to R1 plus R2. Okay, what happens if you are given a circuit which look something like this? E1 positive, E2 positive. So this is negative. So how do we solve, right, this kind of question? Okay, let's now modify the circuit a bit. I'm going to put a galvanometer. So this is a galvanometer. So what is a galvanometer? First of all, let's see. Okay, galvanometer, it points 0 if there is no current. All right, but if the current now flows this way, then the galvanometer will point this way. If the current flows this way, the galvanometer will point this way. So let's look at how the galvanometer works, right? If you have example, if it's like this, what it shows that E1 is equals to E2. The potential difference is the same. That's because the EMF is the same, so the resultant EMF is 0. So if the resultant EMF is 0, the current is 0 in the circuit. Okay? Number 2, if you see the galvanometer moving this way, that means the current is moving in this direction. No, the current is moving in this direction. Okay, anti-clockwise direction. So this means that the E2 is bigger than E1. Okay, sorry, the EMF 2 bigger than EMF 1. Okay, so you have a resultant EMF that provides a potential difference, hence you have a current. So in this case, if it's in this direction, then it will be in the clockwise direction, right? In this case, E1 is more than E2, right? So that's how we interpret a particular circuit. All right, now let's look at how we use Kirchhoff's law to derive the equation for combination of resistors. All right, so if you remember, you would have learned in the previous level, resistors in series, the total resistance is R1 plus R2 plus R3. If you have in parallel, is 1 over R1 plus 1 over R2. So how to derive that equation using Kirchhoff's law? Okay, so if you have resistors in series, example, right? So let's say this is EMF E1, so you have R1, R2, R3. So the current is flowing I, and this will provide a potential difference V1, V2, V3. So as we know, V1 equals to IR1, V2 IR2, V3 IR3. And according to Kirchhoff's second law, the resultant EMF equals to V1 plus V2 plus V3. So let's say in this case there's no internal resistance, so V total, we can say this as V total equals to V1 plus V2 plus V3. So V total, the current times the total resistance, IR1 plus IR2 plus IR3. So cancel this. So what we have, R3. So therefore, we have R total equals to R1 plus R2 plus R3. There you go. Okay, straightforward. Okay, the next part, resistors in parallel. So if you have EMF E, and we have one resistor here, R1, R2, R3, and say now the current in the circuit is I. Okay, and according to Kirchhoff's first law, the current is going to split into I1, I2, I3, and they're going to combine back here. Sum of current entering equals to sum of current leaving the junction. All right, so according to Kirchhoff's first law, I total current equals to I1 plus I2 plus I3. But what is I? I1 is V over R1, I2 equals to V over R2, I3 is V over R3. Right? So in this case, the potential difference across these is V1, V1, V2, and V3. And they are all the same. Okay, so since they all are parallel, for resistors R1, R2, and R3 in parallel, the potential difference across each resistors are the same, V. So they are the same. So therefore, I equals to V over R1, V over R2 plus V over R3. Okay, but how about the current? This is the total current. So the total current is the EMF over total resistance. Okay, so we can put here V over RT, so V over R1 plus V over R2 plus V over R3. But why is the potential difference the same? Okay, why is it same as this? Right, so this is V, this is V, this is V, because all of these are connected in parallel to one another. So we can say they are the same and we can cancel them out. And finally, you get 1 over R total, 1 over R1 plus 1 over R2 plus 1 over R3. Okay. Okay. Let's continue with the next part of the DC circuit. Is we're going to look at potential divider. Okay, what is a potential divider? So let's say now you're given a circuit which looks like this: resistance 1, resistance 2, and here you have potential difference V1 and V2. And say there's a question asks you to find V1 in terms of E, R1 and R2. So let's see. Let's assume there's a current in the circuit I and V1 is I, R1. But the question one in terms of EMF, E, R1 and R2. So I is V over R. So V is EMF E, R is the total resistance, R1 plus R2. So therefore we substitute this into here. So what we get is EMF R1 plus R2 times R1. Okay, and we can rearrange the equation R1 plus R2 times V1. Sorry, times EMF. So as you can see here, this VI is dependent on R1. So meaning if you write V2, so V2 would be R2 R1 plus R2 times the EMF, right? So this is what we call as a potential divider equation. You should able to derive this. Okay, so what is the application? What is the application? So this is where we're going to learn about using LDR and thermistor to control a particular switch. Okay, so using LDR and thermistor in a potential divider circuit. So how are we going to use that? Number one, LDR. Okay, let's find out more about LDR. LDR is a light dependent resistor. So it is basically a material or electrical component that the resistance depends on the intensity of the light. So when the intensity of the light is high, that means bright, so the resistance of the LDR becomes very low. When the intensity of the light is low, that means when it becomes dark, the resistance of the LDR increases. Okay, so let's assume that this is the intensity of light falling on it, right? So using this, we can come up with a circuit. Example, we have a EMF E and we have a LDR RL, and there's a fixed resistor, and here is VL. So according to the potential divider equation, VL equals to RL plus R times the EMF. So when the intensity of the light is low, RL will be high. So VL proportional to RL, when this is high, the VL will be high, right? And when I is high, intensity is high, resistance of the LDR becomes low, VL proportional to the resistance of the LDR. When this is low, this becomes low. Okay, and the next component we're going to look at is thermistor. Okay, thermistor. For thermistor, this is the symbol for the thermistor, RT. So this is the thermistor that we are learning is called the negative coefficient thermistor. Negative coefficient thermistor. Okay, now what does that mean? When the temperature T increases, that means when it's hot, the resistance of the thermistor becomes low. When the temperature T becomes low, that means when it's cold, the resistance of the thermistor is higher. Okay, so same thing, we can come up with a circuit. Where we can use this as a sensor. All right, we have to have a fixed resistor RT, and here's the potential. So VT is RT plus R EMF. Okay, so when the temperature is high, VT is proportional to RT. When the RT goes down, this is VT, this will goes down. And when the temperature goes lower, VT is proportional RT, and this resistance goes up, this will goes up. Okay, all right, the next thing is what we call as a potentiometer. Potentiometer. What is a potentiometer and how is it different than a potential divider? Okay, let me give you an example. Let's say now we have an EMF of 10 volt and we have 3 resistors here. Example 2 ohms, 3 ohms, and 5 ohms. And I have a point here A, B, C, and D. Okay. Now let's connect a voltmeter and let's call this connection as X. So my question is that if X is connected at A, then the voltmeter reading would be 0 volt, simply because there is no resistance between this connection here and A. If I connect to B, the voltmeter reading, what will be the voltmeter reading? Okay, let's do a simple calculation first. So we need to find out what is the current. Current equals to 10 divided by total resistance, in this case is 10 ohms. So this is 1 ampere. So this is 1 ampere. 1 ampere passed through the 2 ohms. This will be 2 volts. This will be 3 volts. This will be 5 volt respectively. So if I connect to B, then the reading would be 2 volts. And if I connect to C, so we have to connect across this, that will be 5 volt if I connect to D, the volt reading will be 10 volt, right? So this is something like a potential divider, right? So the question here is that, can I get 1 volt or 6 volt or let's say 5.4 volts in between? No, right? Because this is the only value I can get, right? It's kind of fixed. So hence we can use a potentiometer to get values, or what we call a variation of values, depending on what is the driver EMF. This is what we call as a driver EMF. This is what is supplying to the circuit. Okay, so let's say now we have a wire. Let's draw it again. I want to make it straight. Okay, and let's say this is X, this is Y, and this is 100 centimeters from here to here. And let's say I have a voltmeter, and this is connection C. Okay, so XY is 100 centimeters. So what are we trying to find here is that the VXY, the potential difference across the XY, is 10 volt as well. So we know that V is equals to IR, that means V is proportional to R. R equals to rho L over A. So when this is constant, R is proportional to L. Therefore, we can say that V is proportional to L. So 10 volt is proportional to 100 centimeter. That means 1 volt is 10 centimeter equivalent, or 0.1 centimeter, sorry, 1 centimeter is 0.1 volt. So if C is placed on 60 centimeter mark, okay, so what is the reading? What is the reading of the voltmeter? Okay, so answer, so 10 volt is equivalent to 100 centimeter. 1 centimeter is 0.1 volt. So 60 centimeters, 60 times 0.1, we get 6 volt. There you go. Okay. So what is the application? Application of a potentiometer. All right. One of the application is to find the EMF of an unknown cell. Okay, so how do we do that? So let's say now we have 10 volt, so we get our wire. So the wire is basically placed on a 1 meter rule. This is a meter rule, and the wire is placed like that. So there's a connection. So normally they will use either constant wire or nichrome. Okay, so what I do is that I place the unknown EMF. Let's call this unknown. Then we bring the galvanometer. And we have connection C. So how does this work? So the procedure, move contact C along the wire XY. Number 2, observe the galvanometer and when it shows 0 deflection, also known as null deflection, it means 0. Okay, it goes like that. Stop and measure. Okay, so example, let's say now it stops here. Okay, so we measure the length of this. Example, say C, when C is at 445 centimeters, the galvanometer shows 0 deflection. So what we know is that 10 volt, right? That's 10 volt equivalent to 100 centimeters. 1 centimeter is 0.1 volt. So 45 centimeter is 4.5 volt. Therefore, the EMF of the unknown cell is 4.5 volt. Why this happens? Okay, let's see. We have to use Kirchhoff's second law. So now we know it is for 4.5 volt. So L is 45 centimeters, which is equivalent to, if I take the voltage of XC, it is 4.5 volts. So according to Kirchhoff's second law, the potential difference across these is now the same as the potential difference across these. So the resultant EMF in this circuit is 0. So IR, so I current also 0 amps, so there is no current in the circuit. The galvanometer will show 0 deflection. That is the reason. Okay, all right, so with that I end the chapter of DC circuit. Thank you.